Zener diode. What is this Zener diode? This is also a diode which is heavily doped, works only in the reverse bias. So here it will have a sharp and almost vertical breakdown. So what is this vertical breakdown? We have studied the VI characteristics of a diode. Here this is a voltage in forward bias, this is a current in forward bias. Until reaching this new voltage, the current will be zero. After that, the current increases and afterwards it acts as a conductor. But if you take the reverse current here and voltage in reverse bias, so this will be curve which is measured in microamperes here. This is milliamperes. This is microamperes due to the current due to minority charge carriers. Afterwards, this will be like this. But Zener voltage is heavily doped such that it will have this vertical breakdown. So this is not slightly inclined here. This is exactly at a particular voltage, current increases rapidly. So let us say this is a 0.2, 0.4, 0.6 volts. So at 0.6 volts, current is let us say 10 microamperes. At the 0.6 alpha, it will become 20 micro. At 0.6 alpha, 30 micro. That means current increases rapidly for a particular voltage. This is almost a vertical breakdown and it is having a sharp value here. It is not blunt. Sharp means at the particular value itself current increases. That means for the same voltage, the current through the diode will have different values and that current value increases rapidly, and this voltage is known as breakdown voltage, also known as Zener breakdown. It occurs in junctions which are heavily doped. The first condition is it must be heavily doped and have a very narrow depletion region. Now we know that electric field in a diode between the junctions is V by D, and this voltage, let us say this is 20 millivolts by, and thickness of the depletion layer in a Zener diode is in angstroms. Let us say this is 200 angstroms here. So this is 20 into 10 power minus 3 by, this is 200 into 10 power minus 10. This 10 times, this will be 10 power minus 9 when it goes to plus 9. So this is 9 minus 3. This is around 10 power 6 volt per meter. And even if this voltage is slightly more, this can go up to 10 power 9 or to 8 volt per meter. So this is the electric field that can be produced between the two ends of a junction of a Zener diode. The main difference between the diode and Zener diode is ordinary diode is doped moderately, whereas it is doped heavily, and it also works only in the reverse bias. Now this strong electric field of this much voltage per unit length can rupture or break the covalent bonds between this one, and they can produce these electron hole pairs in this case. So the phenomena of pulling these charge carriers from their atoms is called Zener breakdown. Here I am showing a simple circuit of Zener diode here. In this we have an input DC source here. This is a variable or maybe variable DC source whose voltage varies from 0 to a given value, and this positive terminal of this battery, actually this is a battery, variable battery, connected to N side of a diode, and negative terminal is connected to P side of the Zener diode, and the Zener diode we are denoting this with Z here. Now as P connected to negative, N connected to positive, this is said to be in reverse bias, and a load of load resistance RL is connected across this one. As these two are parallel, the voltage across this branch must be equal to the voltage across the output here. So the output voltage I am denoting this as VO, which is equal to VZ, that is a Zener diode where this breakdown takes place. So this will be the output here. That means output remains constant irrespective of the input voltage or irrespective of the load current also or load resistance also. Let us say this is a variable DC source. If the input voltage is changing, so this is the main current which is dividing into IZ and IL. So from this I can write for currents, the main current is the sum of the Zener current plus the load current. So let me take this as equation 1. Now equation 2, as we know that the voltage across this one, if you take apply the Kirchhoff voltage law here, so we can write V is the input voltage, and here this is I into Rs plus IL into RL. So I into Rs plus IL into RL is equal to the input voltage here. So after that we can also say that the Zener voltage across this one is Iz into the resistance of the Zener diode, but I am not going to write that one. Here, if V changes as the RL remains constant, RL is constant here, we will choose this Rs such that initially Zener diode will be in a breakdown region only. So Rs is chosen that this will be in breakdown region only. So almost it will attain this one initially itself. That means it will be at a breakdown region. It reaches the breakdown voltage also. So RL is constant, IL is also constant here. And always it is used as a voltage regulator. That means the output voltage must be constant. So as this is constant here, IL-RL also called V0 here. So V is equal to IRS plus V0. As V0 is constant, if you differentiate this one, change in the input voltage is equal to change in the current DI into RS. Similarly, as IL is constant here, that is DIL is 0. So we can write from this one DI is equal dou Iz. That means whatever the current that is changing in the input current can be seen in the change in the characteristic in this Zener current. So change in the voltage, input voltage is equal to, in place of this I can write dou Iz into Rs. So the change in the input current is equal to change in the Zener current. So even if the Zener current changes, this is the current that is changing. This output voltage Vz remains constant. This is called Zener voltage which remains constant. So here also you will get the same output. So this is the working principle of Zener breakdown or Zener diode. Calculate the voltage drop across 5 ohms resistance and also current through the Zener diode for the circuit given below. Here the input voltage is 120 and the Zener voltage is 50, and also voltage across this one is also equal to 50 volts. Out of 120, when these two are having 50 volts difference, what is the potential drop across this series resistance? So PD across 5 ohms resistor is equal 120 minus Zener voltage 50, that is equal to 70 volts. If you know the potential difference between these 2 points, then it is easy for us to find the voltage drop across this one. Already we got it as 50. Now what is the current through this one? The current through this 5 ohms is, so let me denote with this I, which is equal to the potential difference by resistance that is connected in series. So this is equal to 70 volts by series resistance is 5. So this is 14 amperes. That means this 120 volts source is giving 14 amperes current through this one. This current will divide as Iz and IL here. So I can write this as I is equal to Iz plus IL. The next one is, what is the current passing through the Zener they are asking. So they want this Iz. To find out Iz, the main current minus current through this load resistance. The main current already we got is 14, but what is the current through the load? So here you can see the voltage across this one is also 50. So voltage across the load is equal to 50 volts, and load resistance is equal to 10,000 ohms. IL is equal to VL by RL, that is 50 by 10 into 10 power 3. This is 5. IL is equal to 5 into 10 power minus 3 amperes or 5 milliamperes. Now I can write this IL as, this is 14 amperes minus 5 milliamperes. So this is equal to 14 minus 0.005. So answer is 13.995 amperes. This is the current through the Zener here. Half wave and full wave rectifier. In a half wave rectifier you are using only one diode, whereas in full wave rectifier you are using two diodes. So here we are using a transformer. The output of the transformer is connected to this diode here, and this is the load resistance, and output can be obtained between these 2 points. Here we are giving AC input here. So after this, the average direct current is given by I naught by pi here in a half wave rectifier, and the average voltage is V naught by pi. The ripple factor is 1.21 here. The efficiency is very, very important here, this formula. 0.406. Resistance of the load by load resistance plus RF is forward resistance of the given diode. Forward resistance of diode. And the form factor is here 1.57, and ripple frequency is omega, and the pulse frequency is half of the input frequency. That means if we give the AC input like this, the corresponding output will be only during the positive half cycle we will get the input. So the input is only positive half cycle, but there is an output during the negative half cycle. So this is the pulses here, or the input and output waves form. But in a full wave rectifier, each and every value will be doubled here. For most of the cases, average current will be 2 times the I naught by pi. Average voltage is 2 V naught by pi. But the ripple factor will decrease to 0.48, and efficiency is also doubled here. This is 0.406 into 2, that will become 0.812, nearly 80%, this is 40% only. And form factor will be reduced by 1.11. But ripple frequency will be 2 omega, and this will be same. That means if there are 2 pulses in the input wave, and you will get the same number of pulses in the output wave here, 1, 2, 3, 4, 5. That means during negative half cycle also it will give the output. Transistor is the transfer of resistor which can be connected in 3 different modes: common base, common collector, common emitter. So transistor consists of 3 regions. This is the middle of this transistor, we call it as base here, and the thickness of this one or area of this one is less, but here you can see this is having maximum area or more area. Maximum area, the part which is having maximum area in a transistor is called a collector. This is a collector. Intermediate area is called emitter here, and the minimum area is called base. And this emitter is a heavily doped region. Emitter is a heavily doped region. This is moderately doped, and this is lightly doped. But as we have transistors, this is a combination of 2 PN junctions. So we have 2 different diodes, transistors. One is NPN transistor, one is PNP transistor. In NPN transistor, the emitter is N region. This emitter is N region, which consists of electrons. Base is the P region, which consists of holes, and the collector is also consists of electrons, but when compared to this one, this is moderately doped, and these are holes. But to represent this one, generally we know that the current flows in the opposite direction of flow of electrons. Here electrons are traveling like this, so current is moving in the opposite direction. So we will denote this as base, this as a collector, this as emitter. Here electrons are traveling from emitter to collector via base. So current is traveling from collector to emitter via base. So this is the direction of current, this is the direction of electrons. So here also I am showing this from base to emitter, from base to emitter. If I show like this is the direction of the flow of the current. So this is the symbol of NPN transistor. Similarly, in PNP transistor, we have 3 different regions. One is base, this one is emitter, this is collector. Here holes are the majority charge carriers in this one, and these are the electrons, and these are the holes once again. So this is moderately doped, this is lightly doped, this is heavily doped regions. So here, as the holes are traveling like this, that is the movement of positive charge, that is the direction of current. So while representing this P and P, so we are going to denote like this. So this is the collector, this is the emitter, and this is the base region. So holes are moving from here to here. This is the direction of flow of current. So this is how we can represent the direction of flow of positive charge or current here. And this is a NPN, and this is a PNP transistor. Let me explain this CB mode. So transistor in CB mode. So in CB mode, this is the transistor, and this is the base here, this is the emitter, and this is the collector. Generally, for more accurate values or for efficiency, we will use NPN transistors only rather than this PNP. So here, this is a base emitter junction, base emitter or emitter base junction, which is connected in forward bias, as it is a negatively charged one, as it is NPN, this is N. So this will be connected to positive terminal, and this negative terminal will be connected to here, and here also this is also N region. Here N connected to positive, N connected to here, N connected to negative here, P connected to positive here. So this is in forward bias. So emitter base junction is connected in forward bias, but this is connected in reverse bias. That is, this is connected to positive with a bigger cell here. This is in reverse bias. For the working of this transistor, always the first junction should be connected in forward bias, the next junction should be connected in reverse bias. In this, we can write the types of current, that is IE here, because electrons are traveling from here to here. So this is IE, which is going up. This is base current. This is a collector current. So this equation can be written as the total emitter current is equal to collector current plus base current. This is IC plus IB. Now, what is the current amplification factor here? The current amplification, also called current gain, current amplification factor, which is given by, this is the output circuit. So this is the change in collector current by change in emitter current. This we generally denote with alpha, and please remember alpha always less than 1 here, because emitter current is bigger than this collector current. So ratio between IC by IB, this is a bigger current, this is a smaller current. So smaller value, bigger value, always less than 1. So this is about current amplification or also current gain in a common base mode. And the latest one, that means the most frequently used mode in electronics is common emitter mode. Here we will collect this emitter here. This is the base. This is the emitter, this is the collector. So this is also NPN transistor. So this is N region, this is P region, this is N region. So this must be, the input circuit should be connected in forward bias. So as it is P, it should be connected to positive terminal here. And this is emitter is common for both input and output circuit. And here, as it is N, it should be connected to plus here. So this is the circuit. So this is common here. That means emitter is common for both input and output. So this is also connected in forward bias, and this one is connected in reverse bias. So emitter base junction is in forward bias, and the emitter collector emitter junction is in reverse bias. So in this, the input current is IB, output current is IC, and this is actually in this direction, and these two will combine to give IE. So here also I can write the same expression what we have written here. IE is equal to IC plus IB. This is equation 1. But what is the current gain or current amplification factor? Current gain beta is equal output current by input current. That is change in collector current by change in base current, and beta always greater than 1. So then after current gain, we can measure the voltage gain also. Voltage gain in CE mode, common emitter mode here. So here we can write AV, that is voltage amplification or voltage gain, is equal to the output voltage, that is VCE by, that is between C and E. This is the output, to the input voltage VBE, delta VBE. This AV can be written as voltage is the current into resistance. So this is a delta IC into RL, where RL is the load resistance here, divided by delta IB into, this is RO, that is input RI here. So this is input resistance that we are connected here. But this is equal to beta, so we can write voltage amplification or voltage gain is given by beta into RL by RI or RO by RI, that is load resistance or output resistance. So this is expression for voltage gain. And similarly we can find out the power gain also. So power gain in this case is given by, that is AP, that is power amplification, that is output power by input power, that is equal to I square R, I square RO by I square RL. So this is the output current, that is IC. This is the input current, that is IB. So this IC by IB is beta. So this is equal to beta square into R output by R input here, or RL also. This is a power amplification. In common base, the current gain or current amplification factor is given by, as it is common base, the output will be IE, that is delta IC by delta IE. And similarly for this one, beta is equal to delta IC by delta IB. These are the current gains. This is in CE mode, this is in CE mode, this is CB mode. What is the relation between alpha and beta, current gains in common base mode and common emitter mode? Here let me take that equation 1 there, which is equal to IE is equal IC plus IB. Now if you write the changes here, the change in emitter current is equal change in collector current plus change in base current. Now if you divide this with the change in collector current on both sides, you can write this as delta IE by delta IC is equal, delta IC by delta IC will be 1, this will be delta IB by delta IC. Here you can see delta IC by delta E is alpha, but this is delta IE by delta IC, which is equal to 1 by alpha, this is 1 plus, this is a delta IB by delta IC, but delta IC by IB is beta, so this must be 1 by beta. So the relation between these two is 1 by alpha is 1 plus 1 by beta, or 1 by alpha is equal to, if you take LCM beta here, this will become beta plus 1. So this can be also written as alpha is equal beta by 1 plus beta. This is the relation between these two. For example, if you solve a problem here, let us say in a common emitter mode beta is 40 here, this is a beta, and a change in base current, let us say 100 microamperes. Find the change in emitter current, question mark. So first of all, as we know this beta is equal to delta IC by IB, I got this value. So from this expression we can write beta is equal to delta IC by delta IB. So delta IC is equal beta into delta IB. So from this beta is 40, this is 100 into 10 power minus 6 amperes. This is 4 into 10 power minus 3 amperes, or 4 milliamperes. This is delta IC. Now I want delta IE. Delta IE is given by delta IC plus delta IB. So delta IE can be written as delta IC plus delta IB. This delta IC is 4 milliamperes or 4 into 10 power minus 3, and delta IB is equal to 100 micro, that is 100 into 10 power minus 6. This is a 0.1 10 power minus 3. So this is 4 into 10 power minus 3 plus 0.1 into 10 power minus 3. Answer 4.1 into 10 power minus 3 amperes.